In this module, we'll discuss about optical isomerism in octahedral complexes. Optical isomerism in octahedral complexes can be due to ligand distribution and asymmetrical ligand. We'll also discuss about octahedral complexes with monodentate ligands and with bidentate ligands. Optical isomerism from ligand conformation and chirality is also possible for the octahedral complexes. We'll also discuss some solved questions in this module and then the physical and the chemical properties of optical isomers. Learning outcomes. After studying this module, you shall be able to know about optical isomerism in octahedral complexes, learn how optical isomerism is possible for octahedral complexes with monodentate ligands. We will also learn how optical isomerism is possible for octahedral complexes with bidentate ligands. We will also identify the structures of possible optical isomers for octahedral complexes with monodentate as well as bidentate ligands. Evaluate the number of possible optical isomers for octahedral complexes. Optical isomerism in octahedral complexes. As we know that the most important criteria for existence of an enantiomer of a molecule is that it should be disymmetric. That is, it can possess other elements of symmetry but must lack SN axis. There are instances of chirality and optical isomerism that do not depend on having 4 different groups attached to the tetrahedral central atom. Indeed, there are 6 ways octahedral complexes to be disymmetric. These are the distribution of monodentate ligand about the central metal, the distribution of chelate ring about the central metal, the coordination of unsymmetrical multidentate ligands, the conformation of the chelate ring, the coordination of a chiral ligand, and the last is the coordination of a donor atom that is asymmetric. Isomerism from ligand distribution and unsymmetrical ligands. Octahedral complexes with monodentate ligand. In an octahedral complex, chiral metal center can be produced by the appropriate arrangement of different types of monodentate ligands. Among numerous ways, some of them are described. Octahedral complex of type M, A, B, C, D, E, F. Octahedral complex with all 6 different ligands. There are numerous ways to arrange 6 ligands around the central metal ion, and this complex will have maximum number of stereoisomers possible. In such a system, it is very difficult to find out the number of isomers possible. For this, Baylor suggested a method for the isomer enumeration, which is as take one ligand A as fixed point of reference. Second, place remaining 5 ligands in other possible positions. Arrange the ligands in such a way that AB, CD and EF make a trans pair. The resulting pair is listed in the first row 1 and first column 1 of the table. Now, to write another isomer, hold one trans pair constant, that means AB, and hold one of the pair constant in the next row C. Continue changing second ligand until done CD. then CE, then CF. The resulting pairs are listed in the column 2nd and column 3rd of the first row 1. In the above steps, 3 isomers are generated that are possible when AB trans pair is fixed and remaining ligands are permuted on the other coordination positions. Now, if we replace ligand B by C and other 4 ligands B, D, E and F are permuted on the other remaining positions, there will be again 3 isomers generated listed in the second row 2 of table shown here. If we continue the process of replacing ligand trans to A and changing the position of other ligands, will give 3rd, 4th, 5th rows of the table shown here. There are 5 rows and 3 columns in this table. Thus, 15 stereoisomers are generated in this way. Now, each isomer listed in the table is disymmetric, but they are not related to each other as mirror images. So, they are called diastereomers. Diastereomers may be chiral or they may be achiral. Thus, this complex will have 15 chiral diastereomers. Now, each of the 15 diastereomers is dissymmetric, will have a non-superimposable mirror image, means enantiomer. Consequently, total 30 stereoisomers are possible for this complex. Octahedral complex of type MA2C2EF. There are 2 sets of identical ligands. The 2 sets are A is equals to B in MABCDEF and C is equals to D in MABCDEF. Only ligands E and F are different. On substituting A for B and C for D in table 1 will generate another table. This is clear from this table that there are duplicate configuration which are shown here. The duplicates are indicated in table 2 by red color. This leaves 6 distinguished configurations, out of which 2 are disymmetric and have enantiomers. For example, diamine, aqua, dibromo, methyl, chromium 3 cation will have 8 isomers. For drawing stereoisomers, we will first fix position of at least 2 of the ligands attached and then rotate the other ligands one by one. In this complex, we will fix 2 bromine ligands on the trans position and then arrange the other ligand trans to each other. Then we can rotate the position of ligands other than bromine. Thereby, we will get 8 isomers. Out of them, 2 isomers form enantiomeric pair, which are shown here. Octahedral complex of type MA2C2E2. There are 3 sets of identical ligands and these 3 sets are A, that means A is equals to B in MABCDEF. C, that means C is equals to D in MABCDEF, and E is equals to F in M, A, B, C, D, E, F. On substituting A for B, C for D and E for F in table 1 will generate another table, and it is clear from the table that there are duplicate configurations which are shown here. The further duplicated configuration is indicated in this table by green font. This leaves 5 distinguished configurations, out of which only one isomer is dissymmetric and have enantiomers. Other 4 diastereomers have plane of symmetry. For example, diamine, diaqua, dichloro, cobalt 3 complex have been resolved into its enantiomers 1 and 2. Other configurations for this complex are having plane of symmetry, so they are achiral. The number of stereoisomers possible for the given complex with monodentate ligands can be calculated using Baylor's method. By this method, possible number of stereoisomers is calculated for different cases and tabulated here. For complex type MA6, total number of stereoisomers is 1, whereas pair of enantiomers is 0. For the complex type MA5B, total number of stereoisomers possible is 1, however pair of enantiomer is again 0. For the complex MA4B2, total number of stereoisomers possible is 2, whereas pair of enantiomers is 0. For the complex MA3B3, total number of stereoisomers 2, pair of enantiomers 0. For complex MA4BC, total number of stereoisomers 2, pair of enantiomers again 0. For complex MA3BCD, total number of stereoisomers 5 and one pair of enantiomer is possible. One pair of enantiomer is possible for this complex. Complex type MA2BCDE, total number of 15 stereoisomers are possible for this complex and 6 pair of enantiomers are possible here. Complex type MABCDEF, there are 30 stereoisomers possible for this complex and the pair of enantiomers will be 15. Complex type MA2B2C2, total number of stereoisomers are 6, whereas pair of enantiomer is 1. MA2B2CD, total number of stereoisomers is 8 and total pair of enantiomer is 2. However, for the complex MA3B2C, total number of stereoisomers are 3 and pair of enantiomer is 0. Octahedral complexes with bidentate ligands. Any octahedral trischelate, whether with a symmetrical bidentate ligand, is chiral and will have optical isomers. Thus, the octahedral complexes containing bidentate or higher chelating ligands can form optical isomers. Octahedral complex of type MAA3. For example, the tris-ethylene diamine cobalt 3 ion is chiral in spite of the fact that the 3-ethylene diamine ligands are identical and are themselves symmetrical. Complexes with 3 rings such as cobalt in 3 can be viewed like a propeller with 3 blades. The structure can either be left or right handed with non-superimposable mirror images. Octahedral complex of type MAA2X2. There will be 2 geometrical isomers possible for this type of complex that can be cis and trans. Cis complex is chiral and will have optical isomers. On the other hand, trans isomer is achiral and will have only one structure. The optical isomers of cis dichloro bis ethylene diamine cobalt 3 complex are shown here. This figure describes the structure of trans complex which is having structure 1 and 2 which are enantiomeric to each other. However, the pair 1 and 3 and second and third are diastereomers or diastereoisomers. Octahedral complex of type MAB2X2. Disymmetry can be introduced in an octahedral complex by adding unsymmetrical bidentate ligand to it as well. For example, the complex diaqua bis glycine copper 2 is a chiral complex. In this complex, glycinate ion can bind to the metal center in 2 ways. First way can be nitrogen and oxygen of one ligand can be cis to each other, and another way they can be trans to the nitrogen and oxygen to the another ligand. All the possible arrangements can give 5 diastereomers, out of which 3 are enantiomers. This means total 8 stereoisomers are possible. Octahedral complex of type MAB3. Any octahedral trischelate with an unsymmetrical bidentate ligand is chiral and will have optical isomers. Thus, the octahedral complexes containing bidentate or higher chelating ligands can form optical isomer. For example, tris-glycinato cobalt 3 complex is chiral. The nitrogen and oxygen of one ligand can be cis or trans to the nitrogen and oxygen of other ligand. Thus, 4 stereoisomers are possible for the complex. The number of stereoisomers possible for the given complex with bidentate ligands can be calculated using Bayer's method. By this method, possible number of stereoisomers is calculated for different cases and tabulated here. Isomerism from ligand conformation and chirality. Coordination complex can be made disymmetric by attaching a multidentate ligand so that the chelate rings thereby formed can exist in more than one conformation. For example, ethylene diamine bound to a metal center creates a 5-membered puckered ring with a 2-fold axis of symmetry. Two conformations are clearly possible for the ring. One is labeled as lambda, another is labeled as delta. It is also clear here that these conformations are non-superimposable mirror images. However, they have little conformational stability, so it is not possible to isolate two optical isomers of a complex such as tetraamine ethylene diamine cobalt 3 cation. Another way of introducing chirality into a coordination complex is to use a chiral ligand. For example, here is a complex which is optically active where SAMH is a zwitterion of S-alanine which is a chiral ligand. Now let us discuss one question in which we have to draw all the stereoisomers possible for the complex which is chiral. The complex is diamine aqua chloro ethylene diamine cobalt 3 complex. For drawing stereoisomers, we first fix position of at least two of the attached ligand and then rotate the other ligand one by one. For the complex, we will fix the position of ethylene diamine ligand and rotate the other. Thus, we can get 6 isomers. Out of them, 2 isomers form enantiomeric pair which are shown here. Now let us discuss physical and chemical properties of optical isomers. Unlike geometric isomers, optical isomers have identical physical and chemical properties such as solubility, boiling point, color, dipole moment, chemical reactivity towards non-chiral reagents. However, they have different optical properties. That means interaction of enantiomers with plane polarized light is different. Summary. In this module, we discussed about optical isomerism in octahedral complexes, enantiomers and diastereomers. Enantiomers have identical physical and chemical properties. However, diastereomers have different chemical and physical properties.
After starting this module, you shall be able to know about optical isomerism in octahedral complexes, learn how optical isomerism is possible for octahedral complexes with monodentate ligands, learn how optical isomerism is possible for octahedral complexes with bidentate ligands, identify the structures of possible optical isomers of octahedral complexes with monodentate as well as bidentate ligands. Evaluate the number of possible optical isomers for octahedral complexes. Before going into the details of this module, we should be aware of the definition of isomerism and the types of isomerism, that is, isomerism in coordination complexes. The compounds having identical empirical formula but differing in their physical and chemical properties are known as isomers. The phenomenon is known as isomerism. Two principal types of isomerism are known amongst coordination compounds. These are, first, constitutional or structural isomerism, and the second is stereoisomerism. Stereoisomerism can be further categorized into A. Geometrical isomerism and B. Optical isomerism. We should also be aware of the term optical isomerism and how optical isomerism is possible for tetrahedral as well as square planar complexes. In this module, we will start our discussion from optical isomerism in octahedral complexes. As we know that the most important criterion for the existence of an enantiomer of a molecule is that it should be disymmetric. That is, it can possess other elements of symmetry but must lack SN axis. There are instances of chirality and optical isomerism that do not depend on having four different groups attached to a tetrahedral central atom. Indeed, there are 6 ways for octahedral complexes to be disymmetric. These are the distribution of monodentate ligands about the central metal, the distribution of chelate rings about the central metal, the coordination of unsymmetrical multidentate ligands, the conformation of chelate rings, the coordination of a chiral ligand, the coordination of a donor atom that is asymmetric. Let us first discuss optical isomerism from ligand distribution and unsymmetrical ligands. In this category, we will discuss octahedral complexes with monodentate ligands. In an octahedral complex, chiral metal center can be produced by the appropriate arrangement of different types of monodentate ligands. There are numerous ways. Several are discussed as follows. Let us first discuss the case of octahedral complex MABCDEF. That is, an octahedral complex where all 6 ligands are different. There are numerous ways to arrange 6 ligands around the central metal ion, and this complex will have maximum number of stereoisomers possible. In such a system, it is very difficult to find out the number of isomers possible. For this, Baylor suggested a method for the isomer enumeration which is as follows. First, take one ligand A as a fixed point of reference. Second, place the remaining 5 ligands in other possible positions. Third, arrange the ligands in such a way that AB, CD and EF make a trans pair as shown in the figure. Now to write another isomer, hold one trans pair constant, let us say AB, and hold one other ligand C constant. This results in 3 possible isomers as shown in column 1. Continue changing the second ligand until done. For example, in the next column, the ligand B has been kept constant. Again, 3 isomers will be generated as shown in column 2. If we continue the process of replacing ligand trans to A and changing the position of other ligands, it will give rise to 3rd, 4th and 5th rows of the table as shown on the slide. There are 5 rows and 3 columns in this table. Thus, 15 stereoisomers are generated in this way. As you can see, isomers listed in this table are disymmetric, but they are not related to each other as mirror images, so they are called distereomers. Distereomers may be chiral or they may be achiral. Thus, This complex will have 15 chiral diastereomers. Now each of the 15 diastereomers are disymmetric and they will have non-superimposable mirror images or enantiomers. Consequently, total of 30 stereoisomers are possible for this complex. Now let us discuss the octahedral complex MA2C2EF. In this complex, there are two sets of identical ligands, that is A and C. Only ligands E and F are different. On substituting A for B and C for D in the table in the previous section, we find that there will be some duplicate configurations. This leaves 6 distinguished configurations, out of which only 2 are disymmetric and have enantiomers. For example, as seen in the chromium complex, we will have 8 stereoisomers. For drawing stereoisomers, we will first fix position of at least 2 of the ligands attached and then rotate the other ligands one by one. In this chromium complex, we will fix 2 Br negative ligands on trans position and then arrange the other ligands trans to each other. Then we can rotate the position of ligands other than Br minus. Thereby, we get 8 stereoisomers. Out of them, 2 isomers form enantiomeric pair. Now, for the octahedral complex MA2C2E2, there are 3 sets of identical ligands, and these 3 sets are A, C, and E. On substituting A for B, C for D, and E for F in the table, there will be duplicate configurations. This leaves 5 distinguished configurations, out of which only one isomer, the 5th one, is disymmetric and has enantiomers. Other 4 diastereomers, that is 1, 2, 3 and 4, have a plane of symmetry. Now let us discuss one example of the system MA2C2E2. As you can see that the complex has been resolved into enantiomers 1 and 2. Other configurations for this complex are not shown. As they have a plane of symmetry, they are achiral. Any octahedral tris chelate with a symmetrical bidentate ligand is chiral and will have optical isomers. Thus, the octahedral complexes containing bidentate or higher chelating ligands can have 4 optical isomers. Now let us discuss the first. Octahedral complex MAA whole thrice, that is an octahedral complex having 3 identical bidentate ligands. The tris ethylene diamine cobalt 3 ion is the example of this type of system. As you can see that tris ethylene diamine cobalt 3 ion is chiral, in spite of the fact that the 3 ethylene diamine ligands are all the same and are themselves symmetrical. Complexes with 3 rings, such as the cobalt complex, can be viewed like a propeller with 3 blades. The structure can be either left or right-handed with non-superimposable mirror images. Now let us discuss another system, that is the octahedral complex MAA whole twice X2, where A is a bidentate ligand. As you can see, there will be 2 geometrical isomers possible for this type of complex, cis and trans. Cis MAB whole twice X2 is chiral and will also have optical isomers. On the other hand, trans MAB whole twice X2 is achiral and will have only one structure. The optical isomers of the cis cobalt complex are shown on the left side. However, figure on the right side of the slide describes the structure of the trans cobalt complex. Structure 1 and 2 are enantiomers to each other. However, the pairs 1 and 3 and 2 and 3 are diastereomers. In the case of octahedral complex MAB whole twice X2, disymmetry can be introduced by adding unsymmetrical bidentate ligand to it. For example, the copper complex being shown is chiral. In this complex, the glycinate ion can bind to the metal center in two ways. First, nitrogen and oxygen of one ligand can be cis, or second, they can be trans to the nitrogen and oxygen of another ligand. All possible arrangement can give 5 diastereomers, and out of which 3 are enantiomers. This means total 8 stereoisomers are possible. Now let us come to the octahedral complex AB whole thrice, where AB is a bidentate ligand. Any octahedral trischelate with an unsymmetrical bidentate ligand is chiral and will have optical isomers. Thus, the octahedral complexes containing bidentate or higher chelating ligands can form optical isomers. As you can see that the tris glycinato cobalt 3 complex is chiral. The nitrogen and oxygen of one ligand can be cis or trans to the nitrogen and oxygen of another ligand. Thus, 4 stereoisomers are possible for this complex. Now let us come to the next topic, isomerism from ligand conformation and chirality. Coordination complex can be made disymmetric by attaching a multidentate ligand so that the chelate rings thereby formed can exist in more than one conformation. For example, ethylene diamine bound to a metal ion creates a 5-membered puckered ring with a 2-fold axis of symmetry as shown. 2 conformations are clearly possible for the ring. One is labeled as lambda and the other is delta. It is also clear from the figure on the slide that these conformations are non-superimposable mirror images. However, they have little conformational stability, since there exists low energy barrier for ring inversion. So it is not possible to isolate 2 optical isomers of a complex. Just like the previous case, we will fix here the position of ethylene diamine ligand in this cobalt complex and rotate the others. Thus, we can get 6 stereoisomers. Out of them, 2 isomers form an enantiomeric pair. In this module, we have learnt about optical isomerism in octahedral complexes, enantiomers and diastereomers. Enantiomers have identical physical and chemical properties, and we have also learnt that diastereomers have different chemical and physical properties.